Uh, uh, third class lever.
That is correct.
Okay.
Okay. The question states Jeremy fire a baseball as far as he can. His arm is operating. So you probably do overhand throw, right?
Yes, sir.
All right. So how many lever systems are there?
How many levers? I'm sorry.
How many lever systems are there?
To be honest, I don't know. I don't have that as a topic.
Three. There
Okay.
are three lever systems. All right.
Yes,
You have
sir.
class 1, class 2, class 3. And the question stated Jeremy chucks a baseball as far as he can. His arm is operating as a first, second, third, fourth. A fourth class lever does not exist. So, not in the realm of
Oh.
lever systems. So, the fulcrum is in the middle in the class 1. We have an effort arm and we have a load arm. And a seesaw is the best example of the situation. Then we have a second class where the load is exerted downward and the effort is opposite the fulcrum, and that goes upward. And then finally, we have the effort load. Okay. So if I was going to throw something like as far as I can, I'm going to throw it overhand. So the fulcrum is here, the effort is here, and the load is in my hand.
Okay.
So that's why it's a third class lever system.
Okay.
Alright. This is a good one. "15 joules of work were expended moving an 18-kilogram block. What velocity did the block move?" Now, what is the closest formula you think this relates to?
It sounds like it relates to the force formula.
No, because
No.
force equals mass times acceleration.
Okay. Then the power formula.
No. When you were applying for a job, what were you applying for? Or what are you contracting to do?
To do data entry.
Okay, which is a job, which is work, right?
Okay.
So
yes,
that's why I'm just saying formula for work.
Gotcha. This a lot of missing. Okay. Work.
What's the formula for work?
1 second, sir. Apparently I don't have. This is why I needed you, because I'm here writing a bunch of notes for stuff that I don't actually need.
Okay, so it's on the board. Work equals force times displacement. Work is in joules.
Okay.
The force is in newtons. And displacement. But, you know what? Work, force, displacement, 15 joules of work does not necessarily 18-kilogram block. All right.
Okay.
So, kinetic energy is probably the best way to go with this. All right. So, 1/2 mv squared, because we have a mass. We're trying to find a velocity, and that velocity is going to be a result of joules expended. So, let's come back to kinetic energy, 1/2 mv squared.
Okay.
All right. So our mass is 18 kilograms, right? and we're trying to find our velocity squared. 1/2. And we expended 15 joules, 15 joules. So that works in this situation. All right. So how do we get rid of all of this? This is a lot, isn't it?
It is.
All right. And I kind of have it like in chicken scratch. So I'm going to clean it up and make it look a little bit cleaner.
No, you're okay.
1/2, 18. V is the unknown squared. So what is one way that I can get rid of that this fraction? Because that fraction is always a problem.
Yes. I'll say multiply on both sides.
Multiply what?
The 2. So multiply 2 on both sides to get rid of it.
This times this times this. 9. Divide by 9.
Divide by 9.
No. I'm just thinking out loud.
Okay.
So we plug in the box weight and the work done. 15 joules. All right.
Okay.
When we get that, we could do this a couple of ways. I could multiply this times this. That would give us 9, right?
Yes, sir.
What's 15 divided by 9?
3. No.
No. Woo, girl.
I know.
1960 point 60 45 54 1.6. 1.6. And in the interest of time, what the heck? If we continue this will take us down to 1.3.
Okay.
Basically, so 1.3 meters per second is the correct answer.
Okay.
Just meters per second. I'm looking for my little scientific calculator thingamajig.
Okay. While you're doing that, I have a question. So if
The reason.
formula.
Okay, so let me just break it down. I multiplied 18 times the half. That gave us 9. I divided 9 on both sides. 15 divided by 9 is 1.6. So v squared is over here by itself. So 1.6 equals v squared. V is equal to the square root of 1.6. So v is equal to 1.3. If you square 1.3, you'll get 1.6. So that's why it is the speed or velocity. Sorry.
Okay. Well, my question was, if it's giving you like work, why did you use that formula instead of the work formula? Is it
because work is equal to kinetic energy?
I'm lost.
Work is equal to kinetic energy, which means any work that's done to accelerate an object is converted into kinetic energy because it was moved. Kinetic energy is energy in motion.
Right.
So what did I say to you? I said to you that work is equal to kinetic energy. In order to get kinetic energy, what has to happen?
You got to do some work.
Well, you got to do some work. So work is equal to force times displacement. Right?
Okay.
So displacement was going to be done in order to move this 18 kilogram block.
Yes, sir.
We didn't say how much. We didn't say how far we moved it. We just say how much work was done in joules. All right.
Okay.
So
yes, sir.
Kinetic energy is 1/2 mass times velocity squared. All right. So
yes, sir.
the work energy, this is called the work energy theorem. So if work is equal to kinetic energy, we could say kinetic energy is equal to force times displacement, and we could also say that work is equal to 1/2 mv squared based on what we call the work energy theorem. You could Google that if you like, but it's called the work energy theorem. Work is equal to kinetic energy. So if that is the case, then that's why work is going to be equal to 1/2 mv squared. Once we plug in our mass, 18 kilograms, and on the opposite side, the number of joules that were expended, then we just kind of plug and play and do the math.
Okay, understand.
All right. Now, you want me to run through that? You want me to run through that again? The actual math steps? Or you're okay with that?
No, I was just confused. I'm not used to that formula, but I got it now. Thank you.
No problem. So that's called the work energy theorem.
Okay. Work energy theorem.
Okay, next question. Power is the A, amount of force, B, rate of work, C, energy of an object, or D, difference in resistance.
Rate of work.
Rate of work. You will be right.
Okay.
Sound like a game show host.
That's my prize. That's my pride.
Killing that test.
I know.
Okay. If a large gear drives a smaller gear, which of the following will not occur? A, an increase in rotational speed. B, a decrease in torque. C, a change in rotational direction. Or D, a change in gear ratio.
A, an increase in rotational speed.
An increase in I wouldn't go with that because it says which will not occur. You would get a change in rotational speed. Let's discuss that for a moment. All right. Let's say we have a larger gear with 75 teeth, and then we have a smaller gear with 25 teeth.
Okay.
This gear can expect an increase in rotational speed. Actually, the gear ratio is 3, and this will spin 3 times as fast. The smaller gear.
Okay.
So that's why you can't.
My thought was it would take, I guess, longer, so it would slow down.
But the gear ratio here is 3 because you have 3 times as many teeth on the larger gear. So you'll definitely get. Then they ask you which of the following will not occur. You'll definitely get an increase in rotational speed. You won't get a decrease in torque. You won't get a change in rotational direction. If this drives clockwise, this will drive counterclockwise. That will not change, or it won't occur. It won't occur. A change in that clockwise counterclockwise thing. That it's not going to change. So, hold on. Change. Well, no, actually, my bad. Let me back up. You will get a change in rotational direction because this will go clockwise. This will go counterclockwise. So the question is, which will not happen? A change in gear ratio is not going to happen.
Okay.
All right. And the gear ratio is 3, and it will remain that way. And that will be the reason why that the smaller gear will rotate 3 times as fast.
Okay. Gear ratio. What if it was like 2 big ones? 2 big.
The gear ratio will be 1 then. If they had the same.
I mean, in terms of that question.
I'm sorry?
In terms of that question, what if it was 2 large gears?
With the same number of teeth?
Yes, sir.
Then the gear ratio, the gear ratio still would not. The gear ratio, yeah, because it would be 1.
Okay. Okay.
Next question. Which of the following is the best example of an inclined plane? A, a screw, B, a slide, C, a swing, or D, a hatchet?
Slide.
Best example of an inclined plane. You chose a slide and you are correct.
Okay. With inclined planes, it's no equation or formula for that. It's just more questions like this.
Not that I'm aware of. I mean, an inclined plane is a simple machine.
Right.
And
Okay.
what simple machines do is they take our input and they take our input of power or energy or power or input force and it multiplies it. That's what gives us mechanical advantage. For example,
Okay.
have we ever talked about why we have wheelchair ramps?
No, sir.
Okay, I'll tell you why. Let's say your cousin sprained his leg, his ankle, right? And you went to this old medical center, and there were some stairs when you got there. These stairs are 3 meters high. Your cousin is, I don't know, 150 pounds. Well, or let's say kilograms, because we're metric, I don't want to mess stuff up. 150 kilograms. And I just threw that number out. I'm not calling your cousin overweight or anything. But 3 meters high and your cousin's 150 kilograms. Okay, well, in the old days when they didn't have wheelchair ramps, how much weight would you have to lift 3 meters?
That his weight plus the chair?
Yeah, 150 kilograms. Okay.
Right.
So let's say we have the same 3 meters and then we have a 30-foot long wheelchair ramp. 30 meters. Sorry. 3 meters high, 30 meters long. And let's get your cousin in that wheelchair. Okay. Do you think you would have to push 150 kilograms of force to get him up that ramp?
No.
No, because the mechanical advantage is 30 divided by 3, which gives us a mechanical advantage of 10. So I only need 15 kilograms of force to move your cousin. So would you rather lift 150 or push 15?
Push 15.
Yeah, a lot easier. And that's why they have wheelchair ramps. The wheelchair ramps at hospitals are very, very long, so you don't have to exert yourself. You can just push your loved one or friend or family, your loved one or, you know what I'm saying, and stuff.
Yes.
So that's really, really good.
Okay.
So. All right. So that was the incline, and now we have our next question.
Okay.
Weight is the blank. Amount of stuff in an object, density of matter in an object, gravity generated by an object, or force exerted on an object due to gravity. Which would you choose?
Gravity generated by an object. No, I'm sorry. I'm lying. I think it's the last one.
It is the last one. And I was going to be like, nah, no. Mass is the amount of matter in an object. Weight is the force exerted on an object due to gravity. All right, so.
Okay.
Like let's be clear, like the politicians always say, let's be clear. Because a lot of people get weight and gravity kind of mixed up. And,
okay.
Just like
so gravity is a type of weight.
It's
essentially ish.
No, well, we just said weight is the force exerted on an object due to gravity.
Right. Okay.
All right. Okay, in terms of force, what makes hydraulic jacks so useful?
The jack spread out force over a large surface area.
No, it's the fact that liquid doesn't compress very much.
Okay. Do you mind explaining, please?
Well, I'm trying to think of a good example. All right. Air compresses because the molecules are spread apart, really. They get a little closer if it's cold air. But liquid, the structure of liquids, the molecules are such that they don't compress very well. So whatever container you have them in, for instance, could you put a gallon of water in a half-gallon container?
Not all of it will fit.
Not all of it would fit. But if you had enough pressure in an air tank, you could take, I don't know, what is the air kind of measured in? Atmospheres, I think. So you could take a large quantity of air and compress it because it's easier to compress. It's just a characteristic of that matter. It's just a characteristic of that matter if it makes sense, if that makes sense. But that's why hydraulic jacks are so useful, because the liquid doesn't compress. It doesn't compress very well. It doesn't compress well. It's hard to compress. It makes sense?
Yes, sir.
All right. Moving along. Energy is A, the power of motion. B, the application of force. C, the capacity to do work. Or D, the opposition of weight.
Energy is the capacity to do work.
Energy is the capacity to do work, and you would be right. You would be right. Good job.
Okay.
This is a good one. Coming at you now. She's left like, Kino. No, it's not that bad. Work occurs when A, force is applied. B, force is applied in a certain direction. C, force is unable to overcome resistance. Or D, force is used to move something over a distance.
I'll go with A. Is it B?
No, not B either.
No.
Come on.
Okay, well.
What is the formula for work? What is the formula for work? That's what you got to think about. What is the formula for work? Tell me. We went over it. Spit it out. Work equals force times displacement. Like talking about like my little sister when she was a baby. Like, spit it out. You know, when they put something in their mouth. You're like, spit it out. My mommy's gonna kill me if I catch you with this and choking or something. So, work equals what? What's above my finger?
Force.
Times what?
Displacement.
Okay, now look at the multiple choice answers again and tell me which one you would pick.
The last one.
The last one. Force is used to move something over a distance. Bang. So a lot of times when you look at these questions, you got to kind of like, hey, well, what is work? Well, work is force times displacement. And then you pick that answer and you're on your merry way.
Okay.
Right.
Don't overthink.
There you go. Don't overthink it. Okay. How is a wedge different from an inclined plane? A, the angles of a wedge are generally smaller. B, a wedge provides more mechanical advantage. C, a wedge compounds force. And D, a wedge is used in motion. Which one would you pick?
I don't really know what a wedge is, but the ones that we used to hold the door, I would go with A.
Okay, so what does a wedge look like? The ones that hold a door.
It's just a smaller form of the inclined plane.
Mm-hmm. Very good. All right.
Okay.
But have you ever used an axe or a knife?
Yes, sir.
Okay, so if I don't drop my dry erase markers too much, I could get along with this, right? If you look at the serrated side of a knife, it kind of looks like this.
Yes, sir.
But what you have are two wedges. All right. So what do you do?
Sir.
What do you do with a knife? Do you just kind of hold it on the bread, or do you kind of use a motion to cut?
Yeah, and you slice through. Yes, sir.
Then you slice through, or an axe. When I take an axe and I.
Yeah.
So which one would you pick based on what we've just talked about?
I would choose a D. It's used in motion.
And that would be the correct answer.
Okay. Okay.
She's like, okay. All right, Keno, I hear what you're talking about. I see you, brother. That brother's smart.
Yes, making sense.
Okay. I think I have your next question up. Simple machines. All right. Simple machines are useful in that they, A, simplify tasks, B, create a mechanical shortcut, C, are easy to design and build, or D, reduce the effort needed to accomplish a task.
D?
Mm-hmm. Yeah, that's what simple machines do. They take our input, give us a mechanical advantage, and make that force greater.
Right. I was gonna choose B, that was gonna be my second choice.
That would have been wrong.
Yeah.
I'm just saying. Don't shoot me. I'm just the messenger. Okay. The measure of quantity in the. I'm tongue-tied. The measure of the quantity of matter in an object is its mass.
Mass.
Boom! You nailed that. You just homed in on that. Very good.
Yeah. Okay. Because they try to catch me on con with like doing mass and inertia and all that stuff, so I had to like understand the difference.
Mm-hmm.
Yeah.
And after this, we're going to talk about Sir Isaac Newton's 3 laws of motion. I see your eyes like, what is he about to talk about?
Right.
That's why I love the video. I can see you, girl.
Because I can't see your face, like I don't remember that you're looking at me all the time.
Oh yeah, because my camera's focused on the board. Or you might have the bottom of my but yeah, I see you, girl. All right, let's move along. All right,
Okay.
What is the advantage of a single pulley?
A.
No.
Oh, okay.
There actually take one more stab at it, and then I'll jump in.
Okay. I would say C.
Diminishes the effects of gravity. Wrong again. It is
Okay.
B as in boy or Bravo. It changes the direction of effort. In a single pulley system, there is actually no mechanical advantage. Most of the pulley systems that we look at, they kind of look like this, and we have our pull side or chain, and then boom. And I tell you to determine the mechanical advantage by using what I call the horizontal line test. So if I take a horizontal line, move it through here, not counting the chain or pull rope, then the mechanical advantage is 2. MA is equal to 2. So I only need 100 pounds of pull force in order to lift 200 pounds. Isn't that great?
Yeah.
Okay. But the horizontal line test, we have, 2 lines or 2 pulleys. But in a single pulley system, a great example of that is our flag poles. So, sure, that's down you. Let me put your pretty hair in there. And, okay. So there's one pulley up here. And you have your rope that goes up and down. Okay. So you're kind of pulling it, kind of like a clothesline type situation, right?
Yes, sir.
There's only one pulley. And even when we do our horizontal line test, you don't count the rope that you're pulling. So this would be the pull rope. Boom. So it's a mechanical advantage of one. It's not multiplying your force. It's the same force. So it's just changing the direction of your effort. All right?
Okay. Yes, sir.
If I pull one of these lines down, what happens to the flag? The flag goes up. Up. So I'm pulling down in order to drive the flag upward.
And then to bring it down, then I'm going to have to pull up.
Well, I mean, it depends on what rope you pull because, all right, let's just say we have this flag here, right?
Okay.
It would make more sense. Oh, say, can you see? I'm sorry, got a little patriotic there. Okay. To me, there's no pulley on the bottom, right? There's just the pulley up here on a flagpole type situation. All right, so I'm going to pull down to drive the flag upward.
Yes, sir.
Now, since the pulley is upward, if I want to bring it down, I can just pull this downward.
Oh, that's right.
So when we raise the flag, we're actually changing the effort of our direction.
That's the only thing that's changing. Okay.
Okay. Sir Isaac Newton's 3 laws of motion. You should know these things like the back of your hand. Because I get a lot of debriefs where 3 laws of motion. Definitely saw that on the test. So if you don't know them, don't worry about it. Just make sure you take notes and don't forget them this time or after the day.
Okay, I will.
Okay, do you know Sir Isaac's 3 laws of motion?
Yes.
Okay. Oh, okay. That was confidence. Yes. Like, yeah, play. I know Sir Isaac Newton's 3 laws of motion, my brother. Okay.
I know that.
All right, hit me. Sir Isaac Newton's first law.
Okay. A object at rest will stay at rest, and an object at motion will stay in motion unless acted on by an external force.
Okay, an object at rest will tend to remain at rest. And I'm not saying you said wrong. You hit all the points. An object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an outside force. I'm sitting in this chair. I'm at rest. Nothing's gonna move me unless somebody ran and pushed me out the chair. Do you cook?
Yes, sir.
Do you ever scramble eggs?
Yes, sir.
You ever drop an egg?
Yes, sir.
Okay, so an object in motion, that egg is in motion and will tend to stay in motion until splat. Don't laugh at my artwork either. Until an outside force acts on it. So the egg was in motion, it will tend to remain in motion depending on how tall or short you are. And it will remain in motion until an outside force, i.e. the floor, stops it or acts on it. And by the way, since we're here, this is an inelastic collision.
Inelastic, that sounds familiar.
I know it does. That's why I'm talking about it. You think I just be talking? I mean, I do run my mouth a little bit, but
Not like that.
You think I just be talking? That's an inelastic collision.
Okay.
You ever play pool?
Yeah.
All right.
Talk about that.
All right. So, when the cue ball strikes, and the cue ball strikes one of the balls, right?
Yes, sir.
Boom! They collide on I guess like on a minuscule, like on an atomic level. There is some changing or denting in the ball, but it's not really visible by the naked eye, right? So
Okay, yeah.
this would be the elastic collision because it comes back. Like if something hit my hand, right, my skin's pretty much gonna flex back. All right. So that's elastic, right? Your skin's elastic, right?
Yes, sir.
Okay. So after the collision, my hand kind of returns back to its normal state. Elasticity. All right. Is this egg elastic or inelastic? This collision with the floor.
Inelastic because it
Inelastic
cracks
because it changes its form. Energy is applied,
yeah.
but it's not the same. If someone gets rear-ended, their trunk probably won't open. Something's going to change. So elastic versus inelastic collisions. Okay. So that was Sir Isaac's first law of motion. What about Sir Isaac Newton's second law of motion?
I don't know the word for it. I just know it's
and I'm more particular. In particular, I'm concerned with the formula. Not so much, the mass is inversely proportional. No, because they're not going to go there. She's like, what? What did he say? Okay, so yeah, the formula. In formula, I like to know Sir Isaac Newton's second law of motion.
Okay.
Girl, you're supposed to spit that out, man. I thought you knew. Did you cover your mic? And it looks like you froze.
No. Yeah, when you try to do stuff, that's when people want to call you.
Oh, okay. Yeah,
I'm here.
because you're doing something worthwhile. Yeah, there's always going to be interruptions.
Yeah.
And distractions.
That's what they're trying to do, but they're not winning. No.
Mm-hmm.
Can you see me or am I still frozen?
You're still frozen. But that's just okay. I can hear you.
Okay.
As long as you can see me, that's all that's important.
Yes, I can see you. You're too much.
I know, right? How narcissistic was that? You just got to see me. That's it. Okay, but back on track. Sir Isaac Newton's second law of motion.
Force equals mass versus acceleration.
Who? Hold on. Say that again.
Force equals mass times acceleration.
Time acceleration. You said mass versus. I was like, I never heard of that. I'm like, Schroeder developed a new law of motion. Mass times acceleration. Very good. Okay. So forces in what units?
Newtons. Look at me.
Mass is in what units?
Kilograms.
Kilograms. And acceleration is in what units?
It is in, hold on, seconds over meters squared.
Whoa. I like meters per second squared.
Meters per second squared.
Yeah, I don't know what you was trying to say. All right. Now, since we're talking about acceleration, let's talk about the acceleration of gravity.
Okay.
All right. What is the acceleration of gravity in U.S. customary units or British units as opposed to metric units?
The British units is 132 feet per second.
No, ma'am.
13 feet per second.
Mm-mm.
It's 13 something feet per second.
On what planet?
No,
I'm always messing with you. You know I'm messing with you. All right, in the metric, it's 32 feet per second squared.
32. I don't know where that one. Okay.
And what is it in metric units?
The 9.8
Yeah.
Meters per second.
9.8 meters per second squared. You have to say meters per second squared. It is very, very important because that indicates that there is a pylon, meters per second squared. Every second there's a pylon. So I dropped this object in U.S. customary units. After 1 second, it's going to be falling at 32 feet per second. After the second, it's going to be falling at 64 feet per second. After the next second, was it 96 feet per second? 96 feet per second. So velocity is equal to the acceleration rate times the time in seconds.
Okay.
So now, whether you're working in metric or whether you're working in U.S. customary units or you're working in metric units, so velocity equals the acceleration times time in seconds. Now, what am I trying to get at? What am I trying to say? Okay, so now what I want you to do is tell me in metric units how fast this object is falling after 3 seconds. But I want you to keep in mind, I told you that the acceleration is 32 feet per second squared. So when we talk about velocity, it's just feet per second. Feet per second. Feet per second. The feet per second squared automatically should be triggering in your mind. We're talking about acceleration, a pylon. Something is accelerating or, falling vertically. All right.
All right. So do you want me to use the U.S. or the metric?
The metric. I did 3 seconds for the metric. You trying to steal my answers, aren't you?
You said 3 seconds?
Mm-hmm. And remember your formula. Velocity equals acceleration times time in seconds.
Okay. $29.4.
29.4 what? I always need my units.
Meters per second.
Meters per second. Good. You did not say squared because we were not talking about acceleration. We were talking about velocity. And there's a difference. And you got to be careful because they will put different types of units on the test. And you just see your numbers. You're like, oh, my number. Yeah, that's the answer. And wrong because it's the wrong units.
Wrong unit. Okay.
Okay.
Yes, sir.
All right. So listen, there's really not a whole heck of a lot we're going to get done in 2 minutes, unless you have some really, really quick question.
Not really questions like that per se. I just want to, because I'm going over a bunch of laws that I found on Khan. I just want to verify if it's something I should focus on or if I should just ignore it.
Okay. All right.
All right.
When are you available to meet again?
I can meet tomorrow.
Okay, my schedule's wide open. You pick the time.
5 will do great for me as well.
All right. And our timeline, I need you to put in 5 p.m. Tuesday, 5 p.m.
Okay.
Okay. And I will see you tomorrow. Get that list together so you know exactly what topics we need to talk about, whether it's useful to study or not. Just have it ready so we can get into it.
Okay, I will do that. I'll see you tomorrow. Thank you so much for your time today.
Did you learn something today?
Yes, I did. I learned about levers, working energy. There's 3 types of levers, first, second, and third. I learned about the WorkEnergy Theorem. Work is equals to force times displacement, not distance. I learned about simple machines and the pulley system and how the one pulley system only advantage is to change the direction of the effort. And I also brushed up on elastic and inelastic and elastic collisions.
Wow, that was a hell of a recap.
Yeah, so you did a lot today. I appreciate it.
I know, man. Y'all working me to death. I'm about to call my mama. All right, listen.
You know, I'm always gonna beat us.
I know, right?
Yeah.
All right. I'll see you
All right.
tomorrow.
All right, awesome. Thank you.
All right. Bye-bye. Okay, ladies and gentlemen, that was a really, really good session. It was mechanical comprehension preparation for the United States Navy, United States Marine Corps, or United States Coast Guard OAR, which is the Officer Aptitude Rating. If you are seeking to become a military officer, you are going to have to take this test. And this is non-aviation. Like if you were going naval intelligence, surface warfare officer, or something like that. You will have to take this on the aviation side of things, but it's a test you have to prepare for. It is hard. And you will probably need somebody to tutor you, to help you out, to assist you with it, because you only get 1, 2, 3 times to take it. And so I wouldn't recommend anybody jumping in. And the books alone will not help you. You have to you have to employ a test-taking strategy. Okay? I mean, you could answer all the questions, you can run out of time easily, but if you don't know how to manage your time, or you don't have like a teacher, tutor, or trainer to show you how to manage your time, then you can run into a lot of issues, i.e. running out of time and not answering enough questions to build enough points. So again, I'm Kino with STEM with Kino.com. If you have problems with the ASVAB, if you have problems with the AFOQT, the ASTBE, the OAR, any military aptitude test, that's what I have over 10 years of experience preparing people for. And, hey, I thank you guys for taking time out to watch this video, and I hope it was helpful. If there are any topics that you guys, meaning my subscribers, want me to touch on, just drop a message in the little comment section or whatever. And please hit the like button, and please share and subscribe, because I'm pretty sure you got buddies like in your ROTC unit and things of that nature that will that are interested in passing this test too. So I got a little tongue tied there. I apologize. So, hey, thanks for watching. I'll see you guys on the next one. Take care.